Okay, we'll finish up 2.2.5. We've got matrix A. We want a basis for the null space of A. So what we do is we consider the system of equations of the form AX equals 0. All right, so the null space it's the collection of all vectors which are mapped by A to the 0 vector. In note 2.2.A, it says we could also consider the system of equations HX equals 0. Well, here's why that is. Were we to start, say, with AX equals 0 as a system of equations, that'd yield or imply the augmented matrix A augmented with all zeros, components of a 0 vector. Okay. Now if we'd row reduce that, which we've already done, or Wolfram Alpha's already done, we'd have all these rows bumping into each other and it'd produce what we already had. Of course, as we did row operations with all zeros in that final column, nothing changes there. And what that would produce would be the H matrix augmented with all zeros. So that's H augmented with a 0 matrix. So considering A augmented with a 0 matrix or H augmented with a 0 matrix, it's the same thing. That's the reason note 2.2.A mentions this system of equations. Anyhow, now we've got a system of equations. We're trying to solve that. We want to express this actually in terms of a vector space and a basis for that vector space. So this corresponds to the equations x1 plus 5, 6, x4 equals 0, x2 plus 1/3 x4 equals 0, and x3 plus 1/3 x4 equals 0, aligning the x1s, x2s, x3s, and x4s. So we need to express this in terms of x1 equals, x2 equals, x3 equals, x4 equals. So if we'll write it like that, that produces x1 is -5/6, x4, x2 is -1/3, x4, x3 is -1/3, x4, and x4, well, x4 is just x4. So let's introduce a free variable, as we've done many times dealing with systems of equations. We got a couple of options here on the free variable. I'll go ahead and do the simplest thing, though it yields an answer with some fractions in it, and then we'll see a way to weasel around the sixths and the thirds stuff. So I tell you what, let's let r equals x4 be a free variable. Then we've got the system of equations written, I tell you what, let's write it as a vector. We get the systems of equations translated into, say, the x vector with components x1 through x4 equals -5/6 r, -1/3 r, -1/3 r, and then x4 was just r itself. Or make it look more like spans. Remember, a basis is a linearly independent spanning set. Let's bring the R out front, and then we'll have R times negative 5, 6, negative 1/3, negative 1/3, and 1. I need to tell you where the R comes from, where R is an arbitrary real number. So there's a solution to the systems of equations. We weren't exactly asked a solutions to systems of equations question. We were asked a basis question. So to answer the question about the basis for the null space, we need to interpret that as some sort of spanning set. We were dealing with one free variable, the parameter R that we introduced. So X, solution to the system of equations, is an element of, we've taken all linear combinations of that single vector. So we've got X to be an element of the span of negative 5, 6, negative 1/3, negative 1/3, 1. A basis is a linearly independent spanning set. This is certainly a spanning set. Got to be linearly independent, eh? There's only one vector in it. And hence, a basis for the null space of A is just that single vector. Single vector because back upstream we had one free variable, we had a pivot-free column in matrix H. Had we had two pivot-free columns and two free variables, we get two vectors here, and we'd have a two-dimensional subspace, a two-dimensional null space. And the basis would consist of two vectors, one corresponding to each free variable. But a basis for the null space here is then simply the vector negative 5, 6, negative 1/3, negative 1/3, 1. All right, that's a little unelegant, but that's a basis. You know, I could have played a little trick over here, and instead of letting x4 equal r, I could have let x4 equal, let r equal x4 divided by 6, and it would absorb all of those divided by 6 divided by 3 things. Alternatively, I can view it as taking some non-zero multiple of this, and we'll still have a linearly independent spanning set. My favorite non-zero multiple of this vector is 6. So that'll get rid of all the fractions. Both of these valid answers. I multiply by 6, we'll have negative 5 for the first component, negative 2, multiplying by 6, and we'll have a 6 for the third component. So a basis for the null space of that given matrix A is given by either of those. One a little bit prettier than the other. So we had matrix A with rank 3, dimension of the column space and dimension of the row space. We had matrix A with a null space of dimension 1. That's, add up the dimensions, that's a total of 4 dimensions. That's because matrix A had 4 columns. Here's a little copy of matrix A here. So it had 4 columns, 3 of which in a sense contributed to the row space or the column space, and 1 of which contributed to the dimension of the null space. That's the rank nullity equation.